All right, so in this module, we're going to continue with our construction of the Brouwer diagram, particularly looking at the minor species that we haven't quite gotten to yet, because when we deal with those Brouwer approximations, those imply that those are the dominant species. And so we're going to go circle back around and look at the less predominant species and see if we can address their concentrations and their dependencies on log PO2. And the important thing to keep in mind about these minor or minority species is that the mass action expressions that we developed, we mentioned that they all must be satisfied at all times. So even though we think of, for example, the reduction as tied to the low PO2 region, it also has to be valid and if it's at equilibrium at the high PO2. So we can use multiple mass action expressions in different regions. And so that's because they have to all be satisfied at all times. And so that's what we're going to kind of do in this section is we're going to look at different combinations to solve for what we need. Okay, so let's first take a look at an expression for the intermediate region that we just developed, right? We saw that the oxygen vacancy concentration is equal to that constant, right? We saw that that is the case. And so this is kind of so again, this is what we developed for the Shockey defect. And we also have the expression for the reduction that we initially applied to the low PO2, but again, the K of this mass action expression has to be, if it's at equilibrium, it has to be valid everywhere. And so we had that is equal to this. So if we want to essentially find out in the intermediate region what happens to the other species, then we can use this expression and this expression and work from there. So essentially, if we think about this one, so far we've looked at oxygen vacancies and metal vacancies in the intermediate region, right? We saw that that slope is here, but we haven't yet considered the other two species in this overall diagram of electrons and electron holes, right? So if we look at this expression has VO2, which we have solved over here, but it also has the electrons, right? And so that's why I'm using this. And so if I basically plug in this expression here to account for the VO2, I get that K reduction is equal to Ks to the 1/2, and then equals multiplied by electrons squared PO2 to the 1/2. Because again, both of these expressions have to be valid, and so plugging that in. So now again, I'm looking at this intermediate to start with region. So this was valid in the intermediate region. And so if I solve for the species I now want to solve for, it's going to be electrons. And so if I solve for that, N squared is going to be equal to K red times Ks to the minus 1/2 and PO2 to the minus 1/2. And then take the square root to get just concentration of electrons. That will be K red to the 1/2, Ks to the minus 1/4, and PO2 to the minus 1/4. And same thing, this is a log-log plot, so if I take the log of both sides, I'll get the log of the first constant here, K red, plus the log of the second one, plus log PO2 to the minus 1/4. And again, so this is the constant. This is going to be tied to the slope. And so we see that log of the concentration of electrons is proportional to minus 1/4 log PO2. So in fact, this is the slope again, right? Just like we've done in the other expressions. And so in the intermediate region, the slope of the electrons with respect to PO2 should be minus 1/4. And if we want to look at electron holes, we can see that that will be log PO2 is equal to 1/4 log, this is a plus, just to clarify there, PO2. And so, and if you're wondering where this comes from, keep in mind that we have an expression for intrinsic electronic defects relating N and P. And so that's essentially how we can get this expression down here. So our slope should be minus 1/4 for electrons and plus 1/4 for electron holes. And so just like we've done before, I'm going to switch back over to the slides, and we're going to see if those slopes are what we in fact see in the intermediate region of the Brouwer diagram. All right, so again, we're back here at the slide with the Brouwer diagrams. We're particularly interested in 6.6a because this is the one that matches what we've been working on for the last several modules. And particularly, we're looking at the minor species in the intermediate region. So that's region 2 here. And you can see them here, right? So if we follow the lines, we see that electrons, this is the curve here. So it's decreasing, and then holes, that's increasing. And the slope there is minus 1/4, as you can see from electrons, and plus 1/4. So they crisscross right in the middle for the holes. And so that's what we discovered in the rearrangement that we just looked at. The electrons had a minus 1/4 slope, and so we verified that. And then electron holes have a plus 1/4 slope, and so we verified that by using the expression that we had for oxygen vacancies up here, and then using the K red mass action expression to solve for electrons. And then electron holes, we use the intrinsic electronic approximation to be able to get, the intrinsic electronic mass action expression in order to get the plus 1/4 in that case. And so basically at this point we verified the slopes of all of these major species. We've kind of left off this one here and this one here, but those minor species can also be obtained in similar ways to what we just worked on with these minor species in the intermediate region. So again, this is where the Brouwer diagram comes from. We can derive these from our mass action expressions that have factors of PO2, and it tells us about the concentration dependency on log PO2 or whatever the gas partial pressure may be. And it allows us to look at what are the dominant species, how do they react to changes in partial pressure, and these are important characteristics of what we would want for a ceramic to evaluate its properties, because we'll see that a lot of interesting properties are dependent on, for example, the electron concentration or how many vacancies are in the species. So this is all important information for knowledge of ceramic properties.